Here's another illustration of geostrophic currents. Surface currents near the equator in the Atlantic Ocean. Okay. I'll also show you that example for you to learn that the Coriolis effect starts to become significant within a degree geographical latitude from the equator. So within 50 to 100 kilometers from the equator, it already creates a geostrophic balance. Okay, not directly at the equator, but within a short distance from the equator. And this is how the structure of the sea surface looks like. What creates this structure are Ekman currents in the ocean. We talk about that in the next lecture. So it's the Ekman layers induced by the winds that create this structure. And then the geostrophic balance controls the geostrophic flows in this. So near the surface you have some frictional effects, Ekman layers, plus you have also the geostrophic currents. And they are shown here. You can see that they essentially follow lines of the same sea surface elevation. Okay, and in the oceans, you generally get zonal currents in the open ocean away from boundaries. Okay, and you get either flows that go from east to west or flows from west to east in this situation. And some are called, one is called south equatorial current, one is called north equatorial current. But there's also countercurrent, and that actually runs against the wind direction. We talk about that later on. The sea level elevation itself, you cannot measure from boats or so. You need to have some sort of averaging mechanisms, because we're talking about a 20 centimeter change over 2,000 kilometers. It's a very, very small, because of the high density, it can actually create quite strong currents. Okay, and the current speed in that area can be, in particular the countercurrent, can be quite fast, can reach a 50 centimeters per second or something like that. Okay.